Hey, welcome to Normal Approximations to the Binomial, and I want to start with a question, a burning hot red question here, and that is, why would you do it? Why would you try to approximate the binomial distribution with a normal distribution? I don't know, up here maybe some of these things, which are expressions for what? What is this one? What's the probability of getting 500,000 successes in, what do we got here, 1,000,000 trials? With a probability of a half, all that sort of stuff. Hey, that could be interesting to work out, some large combination expressions like that. Can the calculators do it? Well, in the old days, technology wasn't that good, and these big expressions like this were a bit of a problem. So then we use the normal approximation. Now, there's another reason as well for using it. Come over here, and I think you did this before, back in an earlier section. If you take n and p large enough, then you get this very normal looking distribution. And this is, I think you might remember, when n was 30 and p was a half. We've seen this before. So you would be having an expectation of there that the mean of the distribution would be equal to NP. The mean number of successes would be NP, which would be a half of 30. 30 times a half, which is 15. So I guess we could also work out the standard deviation of this distribution as well, just by using all the scores and the standard deviation formula, and get some measures in here of that point of inflection. So it is possible. There might be a bit of a problem here, and a curve going between integral values. You might need to do some corrections there to adjust it. But it would be interesting because we could use all the properties we know of the normal distribution with the binomial. Things like trying to capture the mean, that sort of thing. Well, let's have a look at how all this develops now. Come down and let's have a look. So we're going to start looking at this one again, just what I said to you a minute ago there. If n is 30 and p is a half, this is the distribution of probabilities we get, the number of successes here, in our train, the number of successes on n trials, and our probability plotted up here. And here we've just discussed the mean, 30 by a half, and the standard deviation. Now this isn't covered in this course, but the standard deviation can be given by square root of np, 1 take p, and that's going to give you a normal distribution, approximate normal distribution here with a 1 sigma either side there. Okay, and this would be our sigma, 30 by a half. So we can establish that. That formula, square root np 1 take p, as the standard deviation of a binomial distribution with n trials and probability p. So let's summarise that result, because we're going to need that. So if x is a random variable binomially distributed, parameters n and p, here's our notation, remember. Then the mean is this, and the standard deviation is that. So that's all actually doable on the binomial itself. So that's a start. We have a mean and a standard deviation. And of course, if we're going to fit a normal approximation to it, we're going to need to incorporate that mean and that standard deviation in our normal probability density function. So let's come down and have a look at it working. Let's take the same distribution, and we want the probability of getting 13 successes, and if you did that on the calculator, we would have 0.115. Now if you look at the curve here, this is a continuous curve, so that's why it's an approximation to the binomial. Continuous means all possible values in between integer values are possible. Down here, the binomial has a discrete distribution. You can't have 1.5 successes, you can't have 13.5 successes. So there is a bit of approximating going on here. So let's talk about that. If we wanted to find x is 13, it would be the area under the curve approximated by that. Okay, d by dc. Let's just have a close look at that and get rid of my scribblings here. because on a continuous curve it could be anything bigger than 12.5 successes and less than 13.5. That's the idea. So this is sometimes called, we're not doing this here, we're not doing it properly here, the continuity correction, where we trying to estimate on a continuous curve what the possible values could have been to come to 13 in simple terms. This is not in the course, we're just checking it out here. So the height is h by 1 unit interval, sort of 0.5 on either side of 13, which therefore is h. This is all approximation of this area here. And then if you did that on the calculator to get that 1h value, you get that, which is very close. So you can play around with various things here. You can play with NCD as well, between two limits, and see what you get. But that's the idea. So that's just a very qualitative treatment, really, of what's going on here with approximating a discrete distribution by a continuous one. Okay, so just be aware, mathematics at this level, just be aware of that importance, because that can be asked, the idea of why the normal approximation is only approximation. Okay, let's go and see what we can do with it. Here we are. Okay, so now it's going to answer my question, why do it? Why approximate a normal distribution with a binomial with a normal? Okay, so if the random variable x has a binomial distribution, okay, success, failure, n trials, probability of a success. Okay, approximate it with a normal distribution with mean NP and that standard deviation, because that was the standard deviation of the binomial. So we're going to use that, of course, in feeding into our function. And there is a rule of thumb now. If NP is greater than 10, that's number of trials times probability of success, and n by 1 take p, should have an and in there, is greater than 10. This is a rule of thumb, a rough rule, because not going into the real mathematics of this here, for when it is reasonable to approximate a binomial with a normal. So these are important conditions. If they ever ask you to use a normal approximation, you should check that it's appropriate. NP must be greater than or equal to 10, N1 take P. And then, here it is, here's a breakthrough. The approximate normal variable, which is, here it is, which is normally distributed. The approximate estimation of your x as a normal variable is normally distributed with a mean of 15, and that then from our previous one, that's our 30 times a half, and our previous standard deviation 2.739, so that's our mu and a sigma from above. So that's from the previous example we were doing. So we can say this is the approximate variable which is normally distributed with that. Okay, so can we use this now? Let's use it down here in this problem. A fair coin is tossed 1,000,000 times, so that's a lot of work on a calculating device. They can do it now, so that's not the real reason why we're using the normal. That's going to become obvious in a minute. X is the number of heads, and so x is binomially distributed, and 1,000,000 for the number of trials, 0.5 as probability. So we check here that they're big enough. Oh, yeah, well, we've got big numbers here, so both of them are actually bigger than 10. Find the mean and standard deviation of this binomial variable, NP, and square root of MP, 1 take P, all those big numbers there. Okay, find the probability of exactly 500,000 heads result, and this is going to be our normal approximation here, and there it is, normal. On the Casio, you'll use normal NPD and enter in the same way. So this is what you should do, I guess, if they say to use a normal approximation. The question actually doesn't say that. So in any test or exam, you would just get the calculating device to do the normal BPD, unless otherwise stated, because that's the best way of doing it. This is approximation, and it should say there to approximate it. It doesn't actually say we're going to use a normal approximation there. I guess it hints at it, because it's got these things here. All right, but if you did use an approximate variable here for this one, then what you'd have here is this one here, and we would be able to do it between two values to answer this question here. What's the probability between 499,800 and 500,200 successes? So that would be our way of doing it. This would be NCD. They're not showing that. We've done a lot of that though. So the lower and the upper, the sigma and mean there on the Casio in that order. Okay, how about trying some of these? Let's see what you think now. A recent fitness report claimed that only 50% of young Australians participate regularly in vigorous sports. Okay, so if a random sample of 40 is taken, find probably at 20 of them. So this is a standard binomial, and then in these they're saying use the normal approximation. You're going to use both in this one up here, but in these just use the normal. Okay, so you know that that's what you're about there. Okay, pause the presentation, have a go at those 5. I do all of them because that's all we're going to do with the normal approximation to the binomial as such. Okay, I'll show you the answers now. Okay, 1 term, part of 3 there. 3 and 4. Let's have a look at 5. Okay. Let's move on to something quite interesting in terms of application of the binomial. So here we are. It's called proportions. What does proportions mean anyway? Well, here's the symbol p hat. It's called p hat. When you are sampling from a population and you're trying to find the proportion of the members of the population doing one thing or another. So it is a success-failure thing. This X is binomially distributed. Binomial implies 2 possibilities. And you want the number here divided by the n. So it's a proportion. It's a fraction of the people doing that. So suppose that 247 students from a school of 839 support power. The proportion supporting them is 247 out of 839. And they either do or they don't. We're saying here. Binomially distributed a variable. The probability is the same, 247 over 839, 0.294. So that's the idea, finding the proportion. Often they say, people make claims, don't they, about things like this. So you could go out and test it. So here it is, back up here. You will go out and get a sample proportion, call it p hat, and that will be an estimate of the true proportion in the population who might be doing that. That's what we're doing. Hey, this sounds familiar, doesn't it? We're going to try and trap the proportion like we're trying to trap the mean from before. Okay, and can you see why the course is designed that way? Well, they are the interesting things in everyday life that people make the claims about. On the average, blah, 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 or this many people, or this fraction support us, we got 80% support. All those sorts of claims. Well, here we go. We're going to be able to test claims like that now. So let's have a look at what we're going to do. All right, so here's a little modelling of a proportion type situation. So suppose we have a coin that has a probability of P of turning up heads. Okay, so we're looking for the event heads. Okay, and we've got X is the random variable, is a number of heads. There it is. Here on each trial, on each toss. Now, what are the possibilities? Let's call X1 if the heads turn up, 0 if they don't. So it's a binomial situation here. Okay. And well, the probability of a head is P and 1 take P. What would be the mean of that distribution if you looked at the numbers? I don't know whether you've done this before. What's the expected values here? And it's the size of the variable times its probability. So the mean of this distribution of probabilities is going to be P. Okay. The standard deviation, here we are. Have you seen this before? Again, with expected values and so on. It's the square root of, here's our deviations away from the mean, or the squares, sorry, deviation of the squares, using squares so we don't get positive and negative cancelling out. We discussed that in an earlier presentation. So if you follow through with that, we get square root of p take p squared, square root of p by 1 take p is going to be the standard deviation of that distribution. Okay, so if we do it n times, okay, so take a sample of n from the whole population of all possible throws, and we'll have a sample result like that, and we're saying xi is either a 1 or a 0. We're going to give it a number there, binomial, 2 outcomes. So here we're wanting to add up and find the p hat, so it's all those that were 1s divided by the total here. Okay, so that's x over n. X is the number of heads in n tosses of the coin. Okay, so if we assign it 1, that's just going to be the total x. So we're working with a model here that says the success outcome is a 1, and then the mean of that is going to be this thing here, and x is going to be the number of times that has turned up. Okay, so what have we got then? Well, here we have it. If p hat is a sample of size n, by the central limit theorem, did you see it? P hat is a mean, isn't it? So we can invoke the central limit theorem. Hey, it's all coming back together again. This is why we can use, or it's useful to use, a normal distribution here. Okay, so for sufficiently large n, the distribution of sample means will be around the actual population proportion, and the standard deviation is going to be sigma over root n, and we just said sigma was square root of p, 1 take p, and if we divide that by root n, what do you get? You get, oh, we'll go straight up here. You get that thing there, put it all under the square root sign. So the central limit theorem again can be used here because it is a mean. Okay, and again we have to make sure n is sufficiently large there, and the rule of thumb that we can use again is this, because if that's true, then the original population will be normally distributed, and if we take means from that, then that will be normally distributed as well. So that's just keep in mind what we're trying to do here, that we have to use sufficiently large n for the central limit theorem to apply. All right, okay, so what have we got? Now we've got a normal distribution applied to the proportions in a population. Okay, so let's have a look at what we can do with it. You've seen this before. Hypothesis testing of a proportion. Oh yeah, okay, we did hypothesis testing of a mean. Why can we do this? Because of the normal distribution applying, can't we? Okay, because the proportion's going to, sample proportions is going to approximate the real proportion here. So here, let's say this is a population, and the mean proportion is there, and we're going to take samples and we're going to look at the distribution of the p hats, and the sigma will be less. It'll be, if we looked up here, this would be root p, 1 take p, and a mean of p, and down here we're going to have p is going to be an approximation of our population proportion, and the sigma is going to be square root of p, 1 take p on n, or sigma on root n. Same idea here as what we did before. So using that notion with the central limit theorem, we can say we'll state the null hypothesis, alternative hypothesis, select the confidence interval, significance interval, 5%, confidence interval coming up, calculate the sample mean. Okay, so that's going to be our p hat. Calculate the test statistic, there it is. The z-test is p hat minus p naught, that's the null hypothesis, divided by sigma on root n. And what's sigma? Here it is down here. The sigma of the original population is, and we'll be using in here the proportion under the null hypothesis. Notice here we're going to, the null hypothesis gives us a proposed proportion from which we can calculate, consistent with that, a sigma. We don't need, unlike with the means testing, we don't need a proposed sigma for the population proportion. We can, for the population standard deviation, the initial proportion proposal enables us to calculate it consistent with that. And then we're going to calculate the p-value as before. Remember, it's a two-tailed test. Two-tailed probability of z being greater than or equal to the value or less than, and draw a conclusion. Again, with the hypothesis testing, we say we reject the null hypothesis, or there's insignificant evidence to, insufficient evidence to reject it. Okay, we never say we actually accept it. Okay, so it's the same stuff again, and a normal distribution to the rescue again now. Okay, so let's have a look at testing some stuff now. Okay, so here's an example. In 1997 South Australian election, 35.2% of the voters voted for the Labor Party. To see if this proportion has changed for 2006, a pollster selects 500, N is 500, 198 say they'll vote for the Labor Party. Does this support the claim that the proportions of voters has changed at the 5% level? Okay, what's it supposed to be? Same as before. P0 is 0.352. And the alternative hypothesis, it isn't that. Significant level, 5%. Let's work out the mean from the sample, 198 over 500 voted for them. Oh, it looks like it's gone up. All right? Person in the street might say, oh, yes, it's improved. But is it significant? Okay, or is this a chance variation? Sampling from the original population, which maybe hasn't changed. We're getting a chance variation which is looking a bit higher. We use this one, and then the sigma for the distribution of population, proportion there is that, but then we have to, here's down here, divide by root n, because it's a mean, okay? So we have to divide the population proportion, sigma, by root n. And then finding the difference, 3.396, take 0.352, we get 2.06. And you would all already be able to say something about that. That's too far out, isn't it? So the p-value is z less than or equal to 2.06 or greater than, double it, 0.3094. How do you know that that is outside the rejection region? Because the rejection region is when z is less than or equal to 1.96 or z is greater than or equal to 1.96 from the standard normal curve. Do you remember that? Okay. So we say here, since this figure is less than 0.05, we reject the null hypothesis. And we suggest there has been a change in the proportion of people voting. It is significant at the 5% level, and that there has been actually an increase. Okay, we accept that the deviation is significant and that they have increased a bit. All right, okay. Let's look at Hayes and Harris's comments here, because we're taking screen clippings from Hayes and Harris in this presentation. The calculations are identical to the calculations for testing a mean. The only difference is that we do not have to estimate sigma from a sample. So that's an error. That standard error has come out of the calculation, because P0 will give you a sigma of the population, square root of P0, 1 take P0, and that was going to give us the sigma of P hat, which is square root of P0, 1 take P0 on root n, because it's a mean, which is, you could just go straight to this. You don't have to show all that every time over n. So that's the that's the standard error of estimating the proportions from that. Okay, so let's have a look then. From the null hypothesis we know P0, and we can use this to find the population standard deviation for a binomial distribution from that. Okay, alright, so that's what we've been doing, and let's have a look now at the calculator on this one. Okay, so let's go to stat mode. Here it is. This time intervals, choose F4 and come into this window, choose Z again, F1, and this time single variable sample proportion, this one, F3, we get the one proportion, testing of proportions, and we're testing not equal to. So if it's not equal to, we enter the P0, the hypothesis, then the number of times we get what we want. If we're looking for port power voters or supporters, then we put that number in there and end there. Just watch that. You actually put in the actual numbers, you don't put in a p hat. Okay, then if you hit execute, we have this window, you get a Z score from the hypothesis test, a probability, and they've calculated the p hat for you. Okay, 2/40 has been done there. So just note, you don't actually enter a p hat here. Okay, alright, let's have a look at some problems. Okay, so I want you to pause the presentation, have a go at some problems here. Here's the first 4, and then we'll pop down in a minute and go to the next one. Okay, 5, 6 and 7. Should try and do most of these. Right, I'll show you the answers now, the 7 answers there. Okay, 1, 2, 3. Okay, we go down to 4, 5, 6, see if we can get it on there. 4, 5 and 6. Okay, then the last one, 7's a bit longer. Okay, so have a look and see if that helps you. And just be careful of your statements at the end of an hypothesis test. Okay, let's go on. What else can we do with this idea now? Well, of course, all the normal distribution stuff's going to come up again. And here we go, testing whether a coin is biased. The experimenter decides to toss the coin 100 times. What number of heads must appear for the experimenter to accept that the coin is biased at 5% level? So here we are. Hypothesis is the proportion of heads is a half. Null hypothesis is that it's not. So let's work out what we expect. Our expected p hat sample proportion is number over 100. How many can we put in there? We expect 50, but we know by chance variation it will be less than that or more than that. We don't know. So let's do the test statistic. P hat minus P0 over sigma on root n, which is this thing here. Okay, putting in the numbers. P hat hasn't been done. It's x over 100 take 0.5. And this time, using P0 as a hypothesis of 0.5, we get this in the bottom line here. Now, we reject the null hypothesis as a rejection level, less than neg 1.96 or greater than 1.96. Okay, remember that? This little fellow is saying it here. I'll just go back and revise it on the Z distribution. Okay, the Z distribution has a mean of 0, standard deviation of 1. So there's 68% in there, approximately, and out here at 1.96 sigma, which is just 1 in the Z distribution. Remember, mu of 0, sigma is 1. So in all of that then there's 95%. That's what we're talking about. If you're out in the wings, either the wings, then you're going to be rejected at the 5% level. So, here it is, over here again, that must be less than 1.96 or greater than 1.96. Okay, so multiplying across here, we got less than 0.402 or greater than 0.598, multiplying across and then adding the numbers there. Alright, so multiplying by 100, x must be less than 40.2 or greater than 59.8. So we've got to make those numbers contextual here. So it's less than 41 or more than 59. Okay. Alright, so here it's got to be bigger than 59.8 in actual fact. Let's look at the rounding off there. So if it was bigger than 59.8, really we could argue about whether we'd call that 60 or not, but 59.8, if it exceeds 59, then we're out there, aren't we, in terms of the nearest whole number. And here 41, it must be less than 40.2, so if it was less than 41, the next one is 40, which is too little. That's the idea. 59 is the lowest, and then the next one is 60. So if it was greater than 59, you would be into the next one, 60, which would exceed that. So just think about those things here, whether integral values apply in the problem, and whether the decimal should be round up or down. Okay, so that's important. All right, let's have a look at some problems, 8, 9 and 10 here. Have a go and I'll show you the solutions in a minute. 11. Okay, and then the solutions. 8 and 9. And 10. There's 11. Okay, and you could have expected it. Here it is. We're going to try and trap the actual population proportion, and again the normal distribution to the rescue here. Alright, so let's have a look. If P is a proportion, then we have this. For sufficiently large n, proportion is a mean. So for sufficiently large n by the central limit theorem, we're going to have that, and therefore we can use the same idea again. As soon as we get into that normal distribution situation, so here we have it, I'll flatten that out there, we have a mean of the p-hats equals proportion approximately, and the sigma of the p-hats approximately equal to sigma p on root n, which is the square root of p, 1 take p on n. And away we go. So this is mu plus 1.96 sigma, which the sigma is square root of p, 1 take p on n. And what's down here? 1.96, 95% in here, mu minus 1.96 sigma, which is p, 1 take p on n. So the only thing that's different between this work and what we're doing in the last presentation, or on the one on testing means, is we're varying the sigma of the distribution depending on what we are measuring there, the distribution of proportions, for example, here. So its sigma is different. That's the only difference. The maths is the same. Okay, so it's the mean of the distribution, the sample mean there, plus 1.96 sigma minus 1.96 sigma. Just watch the sigmas. Okay, and with the central limit theorem, remember it's the sigma of the population divided by root n for the means. Okay, let's do some. You'll be pretty good at this because it's just a repeat of what we've done before. We take a random sample of 200. 76 support the Adelaide Crows team. Find the sample proportion of Crows supporters. Let's do it. It's x over n, 76 over 200, 0.38. That's an estimate. They're calling it a point estimate. Estimate of the actual proportion. Find a 95% confidence interval for the proportion who support the Crows. Here it is. Same stuff. Same maths. It's the normal distribution maths. Thanks to central limit theorem. Okay, very important there. Just watch the standard deviations vary for distributions. So the p hat minus 1.96, p hat, 1 take p hat on n. There it is again. And so it's between 0.313 and 0.447. Okay, interpret your answer. We're saying with 95% confidence, the true proportion lies between those two. It could be as low as 31.3% or up to 44.7%. Now, most people would say, this is a person in the street, as soon as you do that survey, this is gospel truth. 76 out of 200, therefore they've only got 38% support. But what we're testing here is the chance variation. If you sample, you're sampling from a distribution, and that may well be a normal distribution or not. When you take a mean of that by central limit theorem, then it's going to be normally distributed, and we're trying to measure this chance variation. And we want to be 95% sure of our result. And that's why you get this enlarged value to 44.7, or down to 31.3. Okay, so the person in the street doesn't tend to understand that. They think, 76 out of 200, that's 38%, that must be true. Of course, if you go back and sample again, you may get variation. That's what we're trying to do here. This is statistics, trying to trap the population parameters, whether it be the mean, or in this case, a proportion. Okay, that the population would really be following. Alright, let's have a look now. Another one. Just little things we can do now that we've got this normal distribution in our heads again. We're wishing to estimate the proportion of households that own at least one dog. Sample 300, found that 123 had at least one dog. Somebody else sampled 600, found 252. Find 95% confidence interval for each sample and comment. Okay, so Jason was 0.41, confidence interval, values, and between 35.4 and 46.6%. Kelly sampling 252 out of 600.42. Interval there, she's done twice as many here, 600. What do you notice? Is the interval smaller? I think it is, isn't it? It's about 0.06, and up here it's almost twice that. So n greater, width smaller. We can see that because we're dividing by root n. So he's got 600, he only had 300. Okay, so the interval widths are different, but what we're interested in is, and here's a little picture, Jason's interval is a bit wider than Kelly's, but what we're interested in is, can we make a conclusion? So one is saying it's between 35.4 and 46.6, and Kelly's a bit tighter there, 38.1 and 46. Okay, so Kelly's large numbers produced a more precise proportion with a narrower interval, but they're not contradictory, are they? They overlap, and so it's quite likely that they both have a good estimate there. Kelly's done better because of the larger sample size. And guess what? That's what we're going to have a look at next. How to reduce the sample size and when we're sampling to trap the population proportion. Okay, come down and have a look at how you do it on the calculator now. So we want to have a interval now. So here, go to stat mode. And if you go to stat mode, we want the interval, and then the z-test, and interval for proportions, and 0.5, and you put it in again, and this time we've got the interval and the p-hat, and so on. Okay, So that's a quick way of doing it, rather than as we did before. We've done it before, back at this stage, I think. There we did it for our mean there. Now we're just doing it for proportions. Okay, same idea on the calculator. All right, so what I'd like you to do now is to have a look at some of these problems. Question 1 to 4. I pause it, have a go. I'll just go down. We've got a few here. 5, 6 and 7. 8 and 9. And I'll show you the answers now. Okay, we'll just come up a bit. 1 through 4. Question 5, fairly long one. 6 and 7. 8 and 9. Okay, let's go on. What else can we do? Okay, all the stuff before with 95% confidence interval again. So if we're given a confidence interval, find what the sample proportion was and the number of samples. So, okay, there's the confidence interval formula again, and one end is this, the other end is that. The p hat is in the middle, isn't it? You're on 1.96 either side, so all you have to do is add up the two ends divided by 2 by symmetry, if you like. Don't really need to write that line in. P hat is in the middle of the interval, 1.96 sigma on one side, neg 1.96 on the other. So P hat is 0.7, add them up, divide by 2, and then in either of the equations, back up here, either of these equations, you can put the P hat, 0.7 minus 1.96 equals that, and then work out the n on the calculator. So there's lots of little tricky things you can do. Some of these are maybe not that relevant, but they're interesting little pieces of mathematics. Come and do some. So 10 and 11, just a couple of interesting little variations there. And let's have a look at the solutions. 10 and 11. Let's do it. You knew it was coming. Choosing the sample size. So you're setting out to estimate a proportion of people voting for somebody or something like that. Then here's our confidence interval. Right, the actual population proportion is trapped between sample proportion minus 1.96 sigma plus 1.96 sigma. So the same maths as before. The width is 2 lots of 1.96 sigma, which is the square root of p hat, 1 take p hat on n. Notice we have to use p hat is coming from the sample. P hat is from the sample. And that would be our width. Let's have a look then. First case. Now, if you haven't got a p hat, because you haven't done the survey yet, if you have and you want to improve the width because, as we found back, Jason was too wide, then you might take your initial p hat from an initial survey, maybe, and do it again with a bigger n so that you can narrow the width down. But otherwise, the p hat has to be p star, which is called an estimate of p. It's an estimate of p, the true population proportion, or p hat, but it's the estimate of the true population proportion. So somebody might say, oh, we reckon we got 30% support. Well, then you might start with 0.30, 30%. So you have to use this formula for the width, using an estimated value, which could be a claim that they're making. Then if we rearrange it all as we did before, dividing by 2 by 1.96, squaring both sides, get rid of the root sign, and then rearranging it, we get this. And of course this is exactly the same as the mean one. The mean one was 2 by 1.96 sigma on W squared. Alright, well that was a population standard deviation, and this would be the same, only this would have in here root P for the sigma of the population would be that, and when it's squared the root sign goes out, so they put it outside. But as you would expect, the maths is identical, the maths is the same. Okay, just watch the sigmas and what they're doing with them. Okay, alright, so therefore we're going to use this to estimate how many people we'll have to talk to get a good estimate of a proportion. Okay, come down. Here we are. A medical procedure is successful in 80% of the patients. New procedure is tried, so we want 95% confidence interval, the width 4%, to estimate the probability of success of the new procedure. Okay, so that's how many people we're going to survey. There's N, 1.96 over W, and the width is going to be 0.04, and the previous procedure was 80%, so let's start working with that. Okay, so P, 1 take P, is that P star R, because we're using an estimate. We're saying we can expect to be about the same, maybe worse or maybe better. We can get a confidence interval and compare later, but we need about 1,540 patients so that the total width is 4%. What does that mean? We'll come up with something like this, 0.82 to 0.78. That's what we mean. We need it tight, 78% to 82%. 4% width. So that's why we have to speak to so many people or test so many cases. Okay, have you got the hang of that? Alright, just spins on the same idea, the properties of the normal distribution. Okay, so let's go to 82 here. So there's 4 questions. Have a go, have a look at each of those and see what you think. Alright, we'll go down to the solutions now. 1, 2 and 3. I think there's 4 all there. Yes, 4 is all there. So mark those. We have a little bit more to do. Hang on in there. Let's go on. Okay, so case 2, we have no idea. No one knows what people think about this situation. There's no p-hat available. Okay. Now, the problem with it is, if we look at the function for the standard deviation, that's that thing there, P, 1 take P, and standard deviation is square root of that on N. We got that, and its maximum value is when, using quadratic theory, when x equals a half. Because this is, what is this? Let's just draw this now. This neg x squared plus x. So here, it's value 1, put it somewhere there, 1 naught, and it's going like that. So the maximum value of that quadratic function is at a half. Okay, so that's going to give us the maximum value of anything like that. Going to have maximum value of quarter, which occurs when p has a half. So this is a bad case scenario when we have no information, because we're going to use p star 0.5, and that's going to give us a maximum value of this. Therefore, n is going to be high. So this isn't a good scenario where you're forced to start with 50-50, not knowing what the true proportion is. And to correct that, you'll have to have a big N to get a good estimate there. All right, okay, so let's have a look at an example now, which is to estimate with a probability of 95%, proportion to within 3% of mosquitoes carrying a virus. Within 3% means 3% on either side. So that is a width of 6%. Just notice that. Within 3%, it's a bit of an English terminology thing here. It means a total width of 6. So put down the formula. There's the formula. There's that. We have no idea, so use 0.5. P star is our estimate, and the width 0.06. We come up with a big number. Sample size of about 1,070. Three significant figures rounding off to whole people. Keep it in context. Now, here we are. What I've been pushing here, the reason that P star 0.5 is not always used. If it's a long way from that, let's just have a look, it's a long way from 0.5, it may result in the sample size n being unnecessarily large. So that's the idea. Try to get some estimate of the proportion before going out and having to survey too many people. Let's have a look at some problems on it, and we'll be finishing up there shortly. So there's question 1, 2 and 3 for you to have a go. And here are solutions for us here. 1 and 2. Come down to 3. Okay. How are you going there? We've got just a little bit more to do. Same as before with the means, testing claims. No, not testing, sorry. Testing is hypothesis testing. Assessing. Nutrition expert found that 43% Victorian children ate insufficient fruit a day. And to compare with South Australia, they sampled 625 and 308 ate insufficient food. So what is that as a fraction or a percentage? 308 over 625, 49%. It looks like we're doing poorly here. We've got, looks like a higher percentage of children not eating sufficient fruit. Okay, let's state the interval there for South Australia, and it says our true population proportion is between 45% and 53% roughly. Now, P equals 0.43 is not in the interval. So therefore, at the 5% level, well, we could say better said, we're 95% sure that the proportion of South Australian children who eat insufficient fruit is different from those in Victoria. And because the Victorian number is lower, we would suggest that our percentage is higher with the 95% confidence, because that's estimating our surety, if you like. Okay, that's not a bad idea. This is not a bad way of doing it, to get an idea of whether there is only chance variation or whether that variation is significant, statistically significant. Is it significant, or is it just by chance? And if it's by chance, then you would expect 43% to actually lie within that interval. Okay, with 95% confidence. Okay, come down and have a go for your last set here. Okay, question 1 and 2. Question 3. And let's look at the answers. There we are, 1, 2 and 3. How are you going? Alright, are you happy with the skills building up here? Let's just do one little bit more. Just a little note here from Hayes and Harris. Important note on confidence intervals. Now, this pertains to proportions mainly. Is it better to assess a claim by examining the confidence interval, or rather to use a single proportion Z test? And with proportions, there's something interesting here. You can get contradictory results, because the Z test uses P0 and the confidence interval uses P hat in the case of a proportion. Therefore, if you have a null hypothesis, you stick that proposal in here, for the P naught and get a sigma. Okay, now if you have a P hat, to get the sigma of that P hat distribution, you're going to need to put the P hat in there. So this is suffering sampling error. We don't know how much error there is there. Whereas over here, this is consistent with H naught, isn't it? Because H naught proposes a P naught proposition or hypothesis, and so the sigma that goes with it would be part of that whole hypothesis. It wouldn't involve an error that is inherent in sampling. Okay, so let's have a look. A report claims that the percentage of car crashes due to drivers being over the legal blood alcohol limit is 12%. From police files, 19 out of 100 were due to drink driving. Comment on the report's claim. Let's use the Z-test. So have a look at the difference here now. It's the claim is 0.12, and so the null hypothesis is the alternative hypothesis is not 0.12. Now, putting in 0.12, Z equals 2.154 P, etc. This is using P equals 0.12 in here in the calculation of the standard deviation. So it's using this. The calculator will use this. And over here we have this estimate 0.19, and going through that they haven't shown the calculation here, but the standard deviation would be 0.19. One takes 0.19 over root n in the z-test, of course, but that's the part of the standard deviation formula for the proportions that we want, the p part there. So here it comes up with interval that and what's the difference here? We have a little bit of a difference here we are, because you've got 0.0312 is less than 0.05, 0.113 up to 0.267. Okay, so here the z-test says reject, and the confidence interval says the 12% lies in there. Okay, so this is a single proportion z-test up here in both cases. The z-test single proportion, so there's an interval, confidence interval here, and a z-test over the other side. But here we should use the z-test because it hasn't got this sampling error in trying to estimate the population proportion. The sampling error is in the standard deviation, and it is based here on a sample proportion. Here it is consistent with the null hypothesis. So if you have a choice, they won't generally do this in tests and exams, you prefer the z-test as a test for a proposed or hypothesis for a proportion because of the greater accuracy in the proposed standard deviation or standard error of proportions. All right, bit hard mathematics there on the end. I hope you've enjoyed these presentations in the inferential statistics and the binomial distribution, and you've got a lot of skills now that you actually can apply in a day-to-day sense when people are making claims. So it is proper mathematics and useful. So I hope you in the future enjoy applying your knowledge there. But for now, cheers from me.